Welcome to video lecture G4. This one is on orthogonal projection in R to the n. I'll be your helmsman, Tom Roby, and here are the outline and objectives. We'll define the orthogonal projection of one vector onto another vector or onto a subspace of R to the n and analyze its properties. And then we'll prove a formula for the projection of y onto the subspace W in terms of inner products. And this will actually look pretty familiar because we've been implicitly using orthogonal projection even in the situation where we were computing the coefficients of, if you expand a vector in terms of an orthogonal basis or an orthonormal basis, that has a particular form. And we'll be using the same properties of orthogonality here that we've been using there, but there'll be a little bit more of a geometrical flavor to it. So the question that we're trying to ask is something that comes up all the time, which is that if you have a vector, how can you resolve it into components? So often in physics, you take a vector and you want to resolve it into a horizontal component and a vertical component. Here, what we want to do is generalize that so that I've got some unit vector, and that's the direction into which I want to resolve one of the vectors, and then the other one should be perpendicular to it. And so really the way I want to think about this is I'm actually projecting not just onto this green vector, but onto the line spanned by this green vector, which I'm sort of drawing in blue here. Okay, so this is the line, the one-dimensional subspace generated by you. And if I want to project onto it, what do? Well, I can take some other color and drop a perpendicular onto this, and I'll call this guy z. This is a vector z. And I'm going to call the vector that so I'm going to draw the projection in the same color, red, that I had before, but you can clearly see that it's different. And so this red or pink vector, now this is the projection, y hat, which is the projection onto u of the vector y. So if a vector has a hat on it, it means it's a projection of something. If it just has the usual vector symbol on it, it means it's that. And so suppose I'm given y, and I want to write y as along this line, so it's some multiple of this vector u, plus something that's perpendicular. So this z vector, the whole point of it is that z is going to be perpendicular to u. And I want to know how to do that in general. And the point is that these conditions give me everything I need to work out a simple formula for it. And the simple formula works like this. I know that z should be perpendicular to u. Well, what's z? Well, z is just the difference. It's y minus y hat, right? So this vector is y hat. So what I'm really looking at is this question of when is y minus y hat equal to perpendicular to u? Okay, so if I'm going to write this way, then, and this y and this cu here, this cu is just another name for y hat. Okay, so this is equal to c times u, and what I've drawn over there. So now what do? Because I want to figure out what c is. I want to figure out how many times I have to go, how many times the length of u, positive or negative possibly, I have to use to get this. So here's the equation I need to write down, which is y hat minus c times u, that's z, right, by this formula. And that needs to be perpendicular to u, which means that when I dot it with u, I should get 0. Okay? Right, this is just saying this vector here is just another name for z. And so what do I get? Well, then this implies that y dot u equals c times u dot u, right? So I just expand y dot u minus cu dot u, and I'll move that over to the other side. And so that implies that c is equal to y dot u divided by u dot u. Okay, and so we've seen this kind of ratio before, right? It occurs in the expansion of things in terms of if you've got an orthogonal basis, then these are the coefficients that you get. So it's the same idea. And so what is that telling me? That's telling me that if I multiply this u by that c, then out here I get CU, and this CU is exactly the projection that I want. Okay, so let's take a look at an example. And so we'll define the orthogonal projection of y onto u as exactly this thing. Y hat is this ratio times the vector u. So this, of course, is a dot product divided by another dot product. That's just a scalar. That's just a real number. Let's find an example to make it real. Suppose y was 4, 7. And I mean, I guess this is actually a pretty good approximation to 4, 7, at least as far as mathematicians go. So that's going to be my y. And I want to project it onto the line spanned by u equals 2, 1. OK, so here's my u, which is 2, 1 in this case. And I want to figure out what the projection is. Well, so let's do it. Do the math, as they say. So the projection of y onto u is equal to, so now I need to take the dot product of y with u. So that's 4 times 47.21 is 8 plus 7 is 15, divided by u1.u1 is 5, right? 2, 1 dotted with itself is 5. That's the length of that vector. And now I need to multiply that times the vector u, which is just the vector 2, 1. So I end up with 3 times 2, 1, or 6, 3. Okay? So that's what this vector here is. This projection vector is actually exactly equal to 6, 3. So I took 4, 7, and I projected it down onto this line, and I got 6, 3. And the idea that we're going to show in upcoming lectures formally is that this point, this is the closest point on this line to that point that's not on that line. And so the applications idea here is that if you have a situation where you don't have exact solutions and you want to find the best possible solutions that find your constraints, then if you're constrained to be on this line, the closest solution you can find if your target is 4, 7 is 6, 3. So that's a very concrete way to think about how this might be practical. Now, as I said before, this is the same formulas for the coefficients when you write y, a vector y, in terms of an orthogonal basis. Basically, what we were doing in that case is just projecting the vector that we had onto each basis vector. And if y can be written in terms of the basis, then that's the right value. If y can't be, it gives us the best approximation to that. So here's the orthogonal decomposition theorem. So this applied, the first thing I did applied to, this is just for one-dimensional subspaces. What happens if we've got more than one subspace? So maybe I should draw a quick picture of the scenario I have in mind, which is now instead of having this vector with just one line below it, I'm thinking of having something like the following. So I think about, I guess it's, I can only really draw 3 dimensions easily. Here's a 2-dimensional subspace in R3. And here's the origin, and now I've got some other vector out here. This is my y. And so I drop a perpendicular down to this plane, and I end up at that point here. So that means that this point, or this vector, if you want to think about it vectorially, is y hat. And what this theorem is saying is that if I have a, so this is my subspace W, if I have a basis, an orthogonal basis for W, so that means that they're all mutually perpendicular, then I might think about that as being like these two vectors. They don't have to be the same length or anything, although they might be. And then this theorem is telling me exactly how I can write this vector in terms of that basis. Okay, so what I'd have to do to write this is I'd have to extend this vector out a little bit, extend that vector out a little bit, parallelogram rule, there you go. Okay, so that's the geometric idea to keep in mind while we're doing all this algebra. So let's look at this theorem for a minute and think carefully about what it says. It says that if I've got y, then I can always find a unique way of writing the vector y as y hat plus z. So z is this orange thing here. So I'm writing it as y, which is part of my subspace, plus z, which is not just not part of the subspace, but perpendicular to it. Okay? So that's why I write z as in w perp. So the claim is that there's a unique way to do that. And what we're really saying is that there's a unique point in this subspace which is closest to that vector. If I have an orthogonal basis for w, then that usual formula applies, except I have to do it for each basis vector. So I'm saying that this, for example, if this is u1, then this length here is y dot u1 over u1 dot u1, right? This vector is this times u1. That's that length. And then the other length would be the same thing with a u2. OK. Right. So now how do you prove a theorem like this? It turns out that the products of orthogonality work really well, that all we need are the basic things about how inner products are symmetric and bilinear and things like that. So let's see, do I have another? Yeah, so here's the start of the proof. So first of all, let's assume that we have a basis. We don't actually know yet that we always have an orthogonal basis for any subspace of R to the n, but that's something we'll prove in an upcoming lecture. So for the moment, let's just assume that we have a basis, and we'll write y hat as above. Okay? So now what I want to do is I want to show that if I use this version of y hat, which I can compute if I have a basis, that in fact y minus y hat, which is z, right? This vector, I want that to be perpendicular to everything here. That's the condition I want. Okay? So let's pick a color and figure out where we're going to write this. So what happens when I take this z, y minus y hat, and I dot it with u sub j, say? Well, this y minus y hat, well, this will be equal to y dotted with u sub j. Sorry, this is a minus sign, minus y hat dotted with u sub j. OK, so y dotted with u sub j I'll leave alone for now. What is y hat dotted with u sub j? Well, y hat dotted with u sub j is this formula dotted with u sub j. So maybe I'll just take this formula, since I'll write it again for you later, and say what would happen if I dot this whole thing with u sub j? Well, it's orthogonal, right? So u1 dotted with u sub j is 0 unless j is 1, and u sub 2 dotted with u sub j is 0 unless j is 2. So it doesn't matter what these coefficients are for any of the values except for the value j. So the only term that's going to survive, and this is really the key thing that makes orthogonal bases so useful when you've got an inner product, is that basically nothing survives being dotted with something except the thing you care about. So this picks out the coefficient of u sub j. All right, so what do you get? Well, when you dot this whole thing with u sub j, the only term that will survive will be the term y dot u sub j divided by u sub j dot u sub j. All of these are vectors. And then it's going to be multiplied times u sub j dot u sub j, right? Because I just dotted on the right with u sub j. And now you just look at that and you say, well, dude, u sub j dot u sub j dotted with that, this just cancels. And I'm left with this expression. And the one other little typo here is that, oh, no, this is fine, right? So then this just becomes y dot u sub j. So now if I look up here, z dot u sub j is just y dot u sub j minus y dot u sub j. OK, so therefore, z dot u sub j equals y dot u sub j minus y dot u sub j. and that's equal to 0. So that's the proof of the orthogonal decomposition theorem. It's not actually hard to show, if you've got an orthogonal basis, that this expression will be something that I can write as y hat plus z with these two things orthogonal. Now the next question, though, is how do I know it's unique, especially because maybe I used a different orthogonal basis somehow. And so here's the interesting thing. To show uniqueness, it actually works better to just use these formal properties that we know. So if I could write y as y hat plus z, or as y1 hat plus z1 hat, suppose I had two maybe different ways to write y in this form, two things which are perpendicular to one another. And one of them is in w, right? Well, I can rearrange this to say, OK, y minus y1 is equal to z1 minus z. Now, y and y1, by definition, are elements of w. So they're differences in w, because it's a subspace. And z, 1 minus z, z1 and z are both in w perp. So they're differences in w perp by definition. So from the left side of this equation, we see this value is in w. From the right side, we see it's in w perp. So it has to be in their intersection. It has to be in both w and w perp. Aha! But we recall that w and w perp only intersect in the 0 vector. Okay? So this last equation here implies that since that intersection is 0, that implies that y hat minus y1 hat equals 0 equals z1 hat minus z, sorry, not hat, just vector here, minus z1. And so therefore, those expressions had to be equal to begin with. So that shows uniqueness. And that shows that at the end of the day, it doesn't matter what orthogonal basis we started with, that this gives us a unique answer. So it must be the right answer. All right, so that's the first slide on orthogonal projections. OK, so that theorem was really functioning both as a theorem and as a definition. So let me just rewrite it here for you. So given a subspace, since we have this unique representation, where we can take any vector y and represent it uniquely as a vector that's on the subspace w here, this y hat vector on the subspace plus something that's perpendicular to it, since we've got this unique representation, we can just define the orthogonal projection to be that unique representation. If we have an orthogonal basis for it, then we can write it this way. The reason that these u1.u, these denominators are in green is just so that you can remember that if we have an orthonormal basis, then the formula gets even nicer because those just become 1. But the formula for just orthogonal, then it is what it is. And the point is that so here's, if I've got this orthogonal basis, u1, u2, then if I look at the projection of y just onto this vector, I would get this value. If I looked at projecting it just onto this vector, I would get that value. And when I add the two, I get y hat. So that's what this equation is saying. And notice that I have two different ways of thinking about orthogonal projection. One is this more formal, but with geometric insight way, where it's just the unique decomposition of a vector into something plus something orthogonal to it. And the other way is given this formula. And it's worth noting that in mathematics, this happens quite a bit, where you can think about something either by defining a formula for it and then proving some properties, or you could define things by their properties and then use those to derive formulas in different situations. That more abstract point of view is often quite useful. A good example of this is actually with the inner product. We define the dot product of two vectors just to be this convolution product, where we multiply things pairwise and add. But we could have defined the dot product in R to the n to be something that satisfied that list of properties that we had back in the initial proposition, the one that showed that it was bilinear and symmetric and positive definite. And often people do that because then it turns out that there are other positive definite symmetric bilinear forms, and for any of them all these theorems apply. So you don't need to reprove a bunch of things. All you need to do is find some other example of a computation that satisfies those properties. Or sometimes you can just derive what the formula has to be from those properties. So in this situation, it's nice that we can go back and forth. the point of the previous theorem is to show that those, first of all, that it existed and that it was equivalent. It didn't matter which way we looked at it. It didn't depend on the basis we chose. Okay, but now let's get very concrete and say, okay, suppose I know that W is the span of these two vectors, and I want to find the projection onto this. So first question is this an orthogonal basis or not? So you have to do the math, right? 2 times 1 plus 1 times minus 1 plus minus 1 times 1 is 2 minus 1 minus 1 is 0. Good. So it's orthogonal. And so now if I want to find the projection, then I guess I've just got to do some computations, right? So I need to find, if I use this formula, I'll get that y hat is equal to y dot u1 over u1 dot u1 times the vector u1. I'm going to leave off some of these vector hat symbols just because they're getting unwieldy. Plus, since I only have two vectors here, y dot u2 over u2 dot u2 times the this I really want to think about as being a vector, so I'll make sure to write it there. And so in this particular case, using these guys as u1 and u2, and this is y, I'll get the dot product of 740 with 2, 1, minus 1. So what's that? That's 14 plus 4 is 18, divided by the length of this vector is 4 plus 1 plus 1 is 6. And now you're really happy because this is an integer, and you know that there's always going to be contrived math problems where integers work out where ordinarily you'd expect to see all kinds of things, square roots and whatever. And this is getting multiplied by u1, which is 2, 1, minus 1. Plus, now what goes here? I dot 740. With this thing, I get 7 minus 4 is 3 plus 0. So I just get 3 divided by the dot product of this with itself is just 1 plus 1 plus 1 is 3. So I'll just get plus 3 over 3 times 1 minus 1, 1. And you work out what that is, and you get, okay, 3 times this plus 1 of these means I get 6 plus 1 is 7. 3 minus 1 is 2. And minus 3 plus 1 is negative 2. Okay, so 7, 2, negative 2 is this vector. And that vector you should think about as being 740. Okay, so it's not a hard formula to apply. And now suppose I said to you, find the projection of 7, 2, negative 2. Well, of course you could use the formula. But we already know that 7, 2, negative 2 lies in W, right? So that means when we project it into W, we'll just get the same thing, right? This is the closest vector in W to it. You can't do any better than that. And this also just follows from when you have an orthogonal basis and you write it out that way. So since this is an orthogonal basis, and this, in this case, 7, 2, minus 2, this vector actually lies in W, we know this is the right formula for giving us the coefficients. Okay, so we know that it's just going to be 3 times this plus 1 times that. So far so good. Now notice that if I had taken 740 and made it an augmented matrix with these two columns, and I row reduce it, I get the identity matrix, although this last one is augmented. Why did we know this already? Pause if you want and stop and think about it for a second. Why did you know that you were going to get the identity matrix here? Why did you know you would get 3 pivots? Okay, well, the answer is that this last thing is saying 0 equals 1, right, which means no solution. So how did we know we would get no solution? Well, this guy is not in W, right? Because when we projected it into W, we got something different. If you project something into W and you get the same thing, then you know you were in W to begin with. But if you get something different, then you know you weren't in W to begin with. Okay, so that means that there was no way to solve this equation. And this is one of the values, as we'll see coming up, of this whole geometry. Then you could ask the question, well, okay, so 740, right, this vector and this vector, they both project to the same thing. What other vectors have the same projection? So for example, I claim that if you took y equals 751 or 762, that all of those would work. How do I know this? Well, the key thing is to think any vector that I get by adding to y hat some multiple of this z will work. Right? So the question is, what z? So let's compute that. Well, z is the vector y minus y hat. Okay, and so y minus y hat, let's just take the first one, right? It's 7, 4, 0 minus 7, 2 minus 2. And so that's 0. 4 minus 2 is 2. 0 minus minus 2 is 2. So I can add any multiple of 0, 2, 2, which is the same thing as any multiple of 0, 1, 1, to this vector, and it will still project to the same thing. And so you notice, right, that 7, 4, 0 and 7, 2, 2 differ by a multiple of 0, 1, 1, but so does 7, 5, 1, 7, 6, 2. Right? Each of these differ by, all I did was I took 7, 4, 0, and if I add 0, 1, 1 to it, I get 7, 5, 1. I add it again, I get 7, 6, 2. Okay? So the point here is that W perp is equal to the span of this z. It's equal to the span of 0, 2, 2. Okay? Now, in general, what would happen if we were like in 4-dimensional space and we were projecting onto a 2-dimensional space? Then we'd have 2 dimensions of things that were orthogonal to W. Right? And then we can't just simply subtract and get a single vector. We'll get a single vector that's in W perp, but it won't tell us what a basis for W perp is. So in general, if we want to compute all the vectors that give us the same projection, then we need a basis for W perp. Probably the best way to do that is to find an orthogonal basis for all of r to the n, and then that starts from a basis, an orthogonal basis from W. We'll see how this process works later. Start from an orthogonal basis for W, extend it to a basis of all of r to the n, and then that extension basis will work, and you can even make it orthogonal or orthonormal if you want. So let's see, I think that may be it. So that's it for the first lecture on orthogonal projections. We'll see in upcoming lectures how they have this nice property of being distance, helping us understand distance minimizing things, and how we can use them for what's called least squares approximation in a little while. Thank you for your kind attention.